distribution, and then afterwards it can sample like conditional distributions and with no computation of the matrix, and it will sample like very large dimension, and I'm going to show it to you. So I made a few calls to this function just to begin with. Here you have some points, for example, that you want to simulate. You want to simulate values of this Gaussian field in a set of discrete points. The ones are here. Here I have some indexes that are representing the ones that I want to say that those are the simulations that will have no condition at the beginning. So I'm not conditioning on those points. I'm going to get an initial sample, and then I'm going to sample from the second set of points, condition it to the first ones. Okay? Can you zoom in? Yeah. That's okay. That's good. Okay. So here, for example, you have this different covariance matrix. All of them are explained in this paper that I referenced over here. And actually, what I did was implement the code that was attached to that paper for Julia. So it's pure Julia implementation. And I did some kind of interpretation of what these people were doing. So here you have, well, you have unconditional simulations over here. Here I'm sampling one scenario at points in X. So if I give the matrix X, it's three-dimensional, this package gives you the values for the numbers of scenarios that you want for all the points. Then condition it to these points, Y. I can sample these set points that are the values, some new scenarios that are conditioned on the previous one. Okay? And here you can also call the function, but with no points, and say how many points you want to sample, and if you want to average some of them in a single point, for example. Yeah. So here I'm telling the function that please sample for me one scenario with 20 points, 20 discretizations on the x-axis, 20 on the y-axis, 3 on the z-axis on depth, and start on the origin 0, 0, 0. And the steps you get from one point to another in the x dimension, it will be 5, 5, and 5 in the y and the z. Okay, so I'm going to show it to you for mining. Okay, so we're not going to go through all that code, but what I'm going to say is that these are very hard problems to solve. Okay, each of these mines can be represented by millions, hundreds of millions of, no, hundreds of millions, but, well, millions of blocks, okay? And you have to take a decision on when to schedule them for many periods, like, for example, 20 years. So it's a very hard problem to solve. Here, what I'm doing is I'm going to sample from using these functions that are made for this kind of mineral deposits. They can also be used for contaminations, like contaminations on the soil, for example. And I'm going to sample some kind of mineral deposit, and then I'm going to extract it optimally. Okay? So here's the model. I'm going to go through the model first. It's very simple. This is a two-stage model for the two-stage formulation. Can you see it well? Like, do I zoom it a little bit? Zoom. Okay. Okay. I think that's too much.
You can hide the Jupyter.
Well, so you have some kind of first stage decision variables here, the x. Second stage decision variables, the y. The x are binary. The x are deciding how which clusters of blocks you're extracting. So you have a first stage decision of where you're going to, which of the blocks you're going to extract, which of the cluster of blocks you're going to extract. And on the second stage, we take a processing decision. So if we extract the cluster C, we can process the block B. And if we process it, we can decide if we extract the copper out of it or just throw it away because it's too poor long. Okay. Here you have a knapsack constraint, some precedence constraints for the clusters, and some knapsack constraint for the processing of the blocks. Okay. So here I'm going to use a package. I'm telling the software a few parameters. Here I'm setting the number of scenarios, and I just call these functions to get the x's, but don't pay attention to them. Here I'm sampling 2 scenarios or NT scenarios from all the points that I want to use to condition the later simulations and the points that I will use later. Okay. So the idea here is that I'm going to sample a single unconditional scenario over here, a single unconditional scenario, and then I'm going to try to reveal it using my functions, right? Using my conditional simulations on the points that I can see. There are these x's over there. So to make it a little bit quicker, I'm just going to skip this. Just trust me, that's for computing the values, the profits of the blocks. So no, don't pay attention. So I sample 20,000 blocks, 20,000 points. 2,000 of them I can see, and 18,000 of them I cannot see. So that will be part of the second stage of the program. Okay. So here is the exact model that is here, written in JuMP for 0.18, sorry. 0.18. Okay, so I'm going to go through this. This one is slow because it's the equivalent determinant formulation of the model, right? So it's very hard to solve. Lead for a stochastic case. This is the vendor decomposition. You can always write the sub-problem and write the dual of this and write it as a cutting plane problem. This is what I did over here. So this is the dual, and I don't know. Well, you can see that the primal is very easy. Once you know which cluster you're going to extract, you just sort the loss of the blocks that you extracted, and you pick the best ones. If you meet these capacity constraints, you're going to have a positive dual variable related to that constraint, so you can calculate it very easily. You just sort the thing. You can solve it polynomial, like n log n. You can solve this problem. Each of these sub-problems, but each of the cuts that you're generating, they can be infinitely many. So that makes sense because it's an NP hard problem. You cannot solve it with a polynomial algorithm. So that's what I wrote here. This is the vendor decomposition. This is solving the sub problem, just sorting the loss, getting the duals. Then when you get the duals, this is the cutting plane formulation. You keep you maintain the key variables, and you just generate these infinitely many cuts. By the way, that's what I meant when I said this is not the most efficient way to do it, because there are way better algorithms and formulations for this specific problem that can use that this beanstalking Zuckerberg algorithm that does column generation. That's way more efficient than this for scheduling with a single period. So here I wrote the master. This is the one that I'm going to add the cuts. And this is the whole function that solves the problem. So that's it. I just set up the mine, set up the precedence constraints, the natural constraints you have on the blocks, that you cannot extract something before extracting something that is above it. And over here, I solve the problems for an instance with 2 scenarios that I generated at the beginning. So here you have the vendors algorithm solving this. I cannot believe that number. Well, that's not the number. Oh, then it's in nanos. Oh well, they need to. No, it's not in nanos. It's in seconds. No, it should take a tenth of that. Something went wrong in all the switching of software, and I'm just going to leave it like this. Perhaps I leave it running. Second, but see if it pops up something different. And the idea is to use this to solve the title of the presentation, to solve this multi-stage stochastic problems with endogenous uncertainty using Julia. So this is the interesting part. I hope I have a minute left. So we are solving this problem that is, well, I have to. Okay, you have many stages. First, on each period, you're going to decide what to extract. On the next period, you're going to observe what you extract, and you're going to update your posterior distributions, and then sample again some sort of scenarios and take any decision, right? But the question is how you approximate the value of these adaptations, right? Of this knowing what's under the ground, some partial information under the ground. So the idea that we propose is something very similar to what is presented in Powell, this approximate dynamic programming that you came out with some function that approximates the value function. All this thing that is on the VT plus 1, you want to approximate that. And what we do is just use two-stage models, these two-stage formulations, to solve the remaining blocks on the mind, but conditioned to what you observe and how it affects the parameters of your distributions. So the problem of that is that now you have a maximization over here, you have an expected value, you cannot take that out of this without some like some strong condition. The conditions are not met because of the endogenous uncertainty here. And so what we do is we do full enumeration on all the possible ways to extract the block, the clusters, right? So there are not too many. You have some production constraints that doesn't allow you to change too much the planification at the beginning. So what we do is we just full enumerate all the possible adaptations that you can do in this thing. And so what's inside that expected value is just this continuous knapsack I showed you before, sorting the loss and getting the best one. Because given the first stage variable, you just need to know how you're going to process all the blocks under each scenario. Okay? So that's the idea, roughly speaking. Well, yeah, this thing won't run, so I'm sorry for all the delay and all the problems that is got to you. I mean, this made you the problems that made you. So that's it.
All right, so we have time for one question.
Well, if you want to, or you know someone that is a geologist or is working on these kind of problems, the idea is to contribute to the community with this library to sample these multivariate normal distributions. So, and this can be used for solving mining problems, like real-sized mining problems. That right now is only commercial.
Have you compared what is the performance of your sampling code versus distribution, the package?
Well, distribution package, one sample 15,000 because there is not enough RAM. Well, maybe if you have a sparse matrix, yeah. But no, I did not compare it. But I have the idea that this is way faster because it never compute the covariance matrix. So it doesn't need that. Just use the law of large numbers, the central limit theorem, to prove that the output of this is multivariate nonlinear. That's the only result that we use. Okay?
Let's thank Tomas.